All right, welcome everyone to the Supercomputing Spotlights webinar series. My name is Hatem El-Tayef. I'm the Vice Chair of SIAM Activity Group on Supercomputing, together with officers Lois McInnes-Kurfman, Rio Yokora, and Michael Bader. We are really excited to host you today. And before we give the floor to our main speaker, I'd like just to remind some of our objectives as an activity group part of SIAM. We'd like to promote outreach and engage and inspire the next generation in HPC task workforce. So the format of those webinars are typically broad, understandable to student and non-expert. I would like to emphasize the HPC impact and opportunities. Our speakers typically come from industry, academy, and national labs. We usually have a rotation between time zones to ensure we have inclusivity. Everyone is welcome to join. So we typically record our session and our webinar and post them on our YouTube channel. So those are the initiatives that officers in this term try to achieve. We want to raise awareness of HPC opportunities and impact, and eventually grow the HPC community. So we have three pillars for initiatives in outreach, in inclusivity, and webinars. I'd like to also emphasize that we are on social media and invite you, to like us, tweet us, and follow us, whichever social media outlet you like. So please also check out our new website. We try to post often, content there and also links to various activities we host as an activity group. So today we are honored to have Professor David Keys from KAUST as our speaker for this Supercomputing Spotlight webinar. So David Keys is a professor of applied math, computer science, and mechanical engineering at the King Abdullah University of Science and Technology, where he directs the Extreme Computing Research Center and where he was founding dean in 2009. He's also adjunct professor of applied mathematics at Columbia, an affiliate of several US national labs. He earned a BSc in aerospace and mechanical sciences from Princeton in 1978 and a PhD in applied math from Harvard in 1984. He works at the interfaces between parallel computing at the numerical analysis and the numerical analysis of PDEs and spatial statistics, with a focus on scalable implicit solvers and exploiting data sparsity. He helped develop and popularize the Newton, Krylov, Schwarz, and additive Schwarz precondition inexact Newton methods. He has been awarded the ACM Gordon Bell Prize and the IEEE Sidney Fernbach Prize, and is a fellow of the SIAM AMS and AAAS. So before I give the floor to Professor Keys, we'll give you, a link for a survey after the webinar, and we'll be really happy to collect any feedback, for us. For more information, as I said, you could really check out our website and take it from there. Right? Without further ado, I'd like to pass now the floor to Professor Keys.
Well, thank you, Hatem, and thanks to the officers of the SIAG on supercomputing for inviting me to give the second lecture in this series. Thanks to all who are joining the webinar, whether very late in Japan or very early in California. I'm very happy to be handed the podium to facilitate a discussion that I think will be increasingly important to the HPC user and developer communities on computational efficiency. And on behalf of the Hierarchical Computations on Many Core Architectures, or HICMA group in the Extreme Computing Research Center at KAUST, I'm pleased to present some ideas that we've been developing on computational efficiency through tuned approximation. You can provide feedback on the content of this talk, in addition to whatever feedback you wish to provide to the SIAG officers, by emailing me directly with any corrections, additions, or updates. My conclusions up front, for those who may need to drop out, are that in our world of environmental and financial constraints, HPC must address the need for greater efficiency as we continue to consume more and more of the world's electricity budgets and laboratory budgets to operate supercomputers. And this is something that we have excelled at historically, and I'll present some trends in hardware efficiency, algorithmic efficiency translated into productive software, and actually, in many cases, redefining the actual outputs of interest in applications to get the science that we need with less computation. And I'll focus mainly on the middle one and on two relatively recent, I mean, within the last couple of decades, maybe, algorithmic opportunities in reduced rank representations and reduced precision representations, which are becoming increasingly important as electricity prices rise and scales approach and achieve actually the exascale. So this journey with tile, low rank, and mixed precision is one that we began about 4 years ago with many applications, and I'll feature one on geospatial statistics that were based on dense symmetric positive definite matrices, in that case a covariance matrix of increasingly large dimensions, such that a traditional n-cubed Cholesky factorization and even storing the n-squared matrix was challenging. So one of the ideas that we adopted, borrowing from the technology of tile algorithms in magma and plasma, was to replace low rank blocks of those tiles with low rank representations. And initially it was a bit of a brute force, and we lived with whatever ranks arose in order to preserve a certain level of accuracy. But eventually we have learned to convert some of those blocks back to a full double in case that the extra overhead of low rank manipulation exceeded the original cost. Now, simultaneously, and in another really swim lane, we were observing that many statisticians actually, when coping with these large data sets, zero out a lot of the blocks, of course, with a proper ordering to begin with, such as a spatial Hilbert ordering, finding that distantly located blocks have weak correlations, and actually took the rather severe approach of band approximations to their covariance matrices. And we reasoned that there were better ways to take advantage of that data by simply lowering the precision with which those small norm blocks combine additively during matrix manipulations with the larger blocks, and their significant digits fall off. And again, originally we just assumed a sort of band structure, but have learned, especially through recent work of Chaim and Mary, which came out in 2022 in Acta Numerica, to actually test each block for its relative norm and according to the norm, use the appropriate precision. And now we are in a software environment on the right, where our single data structure contains blocks of many different types of ranks and precisions. And of course, this spoils the kind of uniformity that we traditionally want in bulk synchronous parallel computing. So we are driven to request improvements from our colleagues in runtime system, dynamic runtime systems. And the message really for y'all is don't oversolve, maintain just enough accuracy for the application purpose, and economize on storage, no extra copies of the original matrix. Now let's see why this is increasingly important by considering an exaflops system. The number 2 system on the green 500 and number 1 on the top 500 is Frontier at Oak Ridge, and it achieves about 1 exaflops at about 50 gigaflops per watt, so about 20 megawatts consumed continuously. At representative consumer costs of about 20 cents per kilowatt hour in the US, this is about $200 per megawatt hour, and for a 20 megawatt system, about $4,000 per hour. And for a 10 kilo hour year, 8,760 to be precise, that's about a $40 million annual electricity bill. But that's not the worst of it. The carbon footprint for a kilowatt hour is now about 0.5 kilogram of CO2 equivalent in greenhouse effect. That's improving, but certainly not as fast as we're demanding more of electric power. And if you multiply that 0.5 kilogram by 20 megawatts, you get 10K kilograms, or a megagram, if you will, of hourly production of carbon from this exaflop system. And that actually is 100 million metric tons of CO2 annually. That's enough to power 20,000 typical passenger cars for a year in the USA with typical miles per gallon and miles driven. So what does that mean? A 10% improvement in computational efficiency, it gives you an extra $4 million a year to invest elsewhere or do more science on the same expenditure. And it takes the equivalent of 2,000 cars off the road for a year. Yes, 2,000 cars off the road or an exascale system. Even 10% improvement of efficiency is significant in an environment like this. What about 10x? And you'll see more than 10x. You'll see even 2 orders of magnitude in certain relevant computations that are equally scientifically useful in the course of this talk. So if we define efficiency for the moment as science per joule in some loose sense, we, again, will consider 3 categories of efficiency improvement: from hardware, from algorithms, and from redefining the application objective. Along the way, we'll introduce what my colleagues call high-performance statistical computing, especially in environmental statistics relating, for example, to the siting of renewable energy with solar, wind, or agriculture with rainfall, moisture, things of that nature. We'll preview a 2022 Gordon Bell finalist to spotlight how kernel linear algebra operations have been made more efficient by exploiting rank structure, which is related to the smoothness of the covariance matrix, and precision structure, which is related to magnitudes. And before we do any of that, we'll briefly review some properties of the Laplacian, which remind us how we got into the double precision default in the first place, and give us some context for the rank efficiency improvements. But first, hardware efficiency. This is tracked for the last decade or so by the Green 500, and you see an extremely impressive set of devices given to us by architects pursuing largely the consumer market. But that last bar is a small version of Frontier on the right there, which is about 62 gigaflops per watt. That's #1 on the Green 500. And you see a 15x improvement in power efficiency per delivered flop over the last 10 years. What about algorithmic efficiency? I like to track this by Poisson solvers. This is a enterprise that we began when writing the scales report with some of you in the audience way back in the year 2001 for the US DOE SIDAC program. So consider Poisson solve in an n by n by n 3D box. The natural ordering gives a bandwidth of n squared to this n cubed of data. And if you do a traditional banded Gauss elimination, such as von Neumann and Goldstein first showed could be done at all in floating point arithmetic back in 1947, that would be n-fifth storage and n to the 7th flops, n times the bandwidth squared on the flops. Over time, in view of the need to solve ever larger Poisson problems, iterative methods took over, and you see a succession, well, you see a quick improvement down to 1 copy of the matrix stored, and the succession of computational flops improvements up until multigrid, full multigrid, which is an order n method for n unknowns, or n cubed in this case with little n. And as for n as small as 64, this implies an overall reduction of 64 to the 4th, or 16 million. In other words, 6 months of computing is reduced to 1 second on the same hardware. So looking at that plotted against Moore's law over the same 36-year period of algorithmic development, that's 36 years means 24 Moore's law doublings, another factor of 16 million. So 16 million from algorithms, 16 million from hardware, assuming that the algorithms live well on the new hardware. But of course, that's for a very small box. And as we make the problem larger, the advancement from algorithms surpasses even that of our hardware. And this is a chart that goes back to Steve Jardin in the Scales report, volume 2, where we looked at the Moore's law once again on this log Lin plot as the blue line, and several advances in algorithms for two different fusion formulations, one with gyrokinetics and one with MHD, and you sort of see a punctuated Moore's law with several dramatic verticals coming from algorithmic improvements. I won't go into the details. The Scales report is still online, We had also a contribution, for example, from detailed kinetics combustion from our friends at Berkeley. And you can see the combustion kinetics in red and the CFD in green, some of the improvements made on standard problems there over Moore's law. So algorithms, as you can see, improve exponents. Moore only adjusts the base. And to scale to extremes, we must start with algorithms which have as close to optimal asymptotic complexity as possible. Optimal means, as many flops as it takes, if you will, to print out the answer where you need it. And these are typically recursively hierarchical, such as the fast Fourier transform, n squared to n log n, multigrid, that last iterative preconditioned CG method down to order n, fast multipole, n squared interactions down to n, sparse grids, an n to the d dimensional domain of finely sampled points represented to equal accuracy by n times log n to the d minus 1 of hierarchically selected points, H matrices taking the n cubed factorization of a dense hierarchically low rank matrix down to n log n squared, randomized matrix algorithms which replaced an n with a k, where k is the actual block, for instance, the rank of a SVD block. And I'm challenging the audience to come up with the wonderful improvement, shaving off a power of n for a log n or a rank or some other order 1 entity for the 2020s. That's your challenge, as posed by one of our former students at Coast, Long Vega. With great computational power comes great algorithmic responsibility. So application efficiency from redefining the objective. Sometimes the traditional output of interest is not the solution to high accuracy everywhere, but a functional of that solution to a specified accuracy, such as a bound on the convective heat flux across a fluid solid boundary, such as you might have blowing a fan across semiconductor chips. This is actually obtainable without solving the fluid mechanics problem to globally uniform high accuracy everywhere, as shown way back in 2001 by an engineering group at MIT, Michiels, Pereira, and Patera, where this convective problem, which to be solved accurately to the fluids would require the almost black intermediate mesh, can give you an equal accuracy heat flux across those heat sinks by the modestly resolved mesh on the right. Another example of application efficiency is using low fidelity surrogates in early inner iterations of outer loop problems, such as optimization, where you just need to take a step in the optimization direction without necessarily solving the PDE accurately everywhere. So to summarize where we are so far, if we want to look for better science per joule, we look to the amazing architectural improvements, the algorithm and software improvements, and application definitions. What are the outputs of interest? In a fortunate world, these are orthogonal. The desired app can employ the best algorithm on the most efficient hardware, all mediated, of course, through high productivity software. So let's take a couple of lessons from the 1D Laplacian before we get into our environmental statistics example for today. I'm showing here the 1D Laplacian for a small uniformly discretized unit interval, actually the negative of it so that it's positive definite for any of the traditional second order discretizations. And the first thing you'll help me remember about the Laplacian is that as you scale it, it has ill conditioning. As you invite more and more Fourier modes to be representable, you drive the ratio of eigenvalues towards extremes. The smallest eigenvalue of that -1, 2, -1 matrix goes like pi over n squared. The largest one approaches 4 as n approaches infinity. And so you have a condition number that grows like the square of the number of points, or like the inverse of the mesh spacing, as is more commonly posed. And in real arithmetic, kappa approaches the reciprocal of machine epsilon for an n as small as 1,000, which is, of course, nothing in today's highly resolved PDE simulations. That's only a billion points only a billion points in 3D. And of course, Laplace-like operators arise throughout modeling and simulation, whether it's diffusion, electrostatics, gravitation, et cetera, even Laplacian graphs. And this implies an order 1 error in inverting the Laplacian in single precision. So HPC has traditionally demanded double precision in its core hardware by default. And GPUs, in fact, were only really accepted when they began to offer double precision in hardware. That was in 2008. Tsubame, the first supercomputer using GPUs, was 2010, and the rest is history. Now, 8 of the top 10 are all based on GPUs with high precision in hardware. Now, for the biharmonic, of course, even double precision gives out with a mesh resolution of 1,000. So some multi-scale codes like Mike Norman's for adaptive refinement in celestial dynamics require quadruple precision, even if it's available only in software. So it's very understandable how we got into this double precision default, but we have to get our way out of it for many applications or many kernels of even ambitious applications that have some ill conditioning in them. The other nice property that we can review based on the simple 1D Laplacian is that of off-diagonal low-rank blocks. Of course, this is trivial for the forward Laplacian because it's essentially a sparse matrix. But what's interesting, and what Fiedler pointed out way back in 1986, is that the off-diagonal blocks of the inverse of such matrices share the same rank. So this is the inverse of the 1D Laplacian, and indeed, all the off-diagonal blocks can be composed as the outer product of 2 rank 1 vectors. And in fact, if you remember anything about Green's functions, you see that these columns or rows, because of symmetry of the inverse Laplacian, are exactly the Green's function for the 1D Laplacian. It's flat between the discontinuity points. So that's where the low rank comes from. And if that were a variable coefficient problem, we might have to suffer, 2 or 3 vectors wide for tall, skinny, and broad matrices instead of single vectors. But that structure is in all of those juicy Laplacians and many other things. So it turns out that many formally dense matrices arising from covariances in statistics, integral equations like Green's functions, Schur complements within discretizations of PDEs, Hessians in optimization, non-local operators from fractional differential equations, radial basis functions from unstructured meshing, kernel matrices from machine learning. These all have a hierarchically, or a tile in this case, low rank structure. In addition, many of these matrices have a decay in magnitudes under a proper ordering, so that nearby points in space are near each other, such as Hilbert. And therefore, when additively combined in Gaussian operations or matrix multiplications by a sort of unit norm vector, many of these outer diagonal blocks, or wherever they happen to live in your given ordering, can be replaced with lower precision without any loss of accuracy in the result, and with a tuned loss of tolerable accuracy. Now, of course, mixed precision algorithms have a long history, 60 years, going back to Wilkinson, where the matrix in a direct solve was stored one way for residual computation and in lower precision for the factorization and update correction. And there are many such new algorithms using up to, believe it or not, 5 precisions in the groups of Hayem and Carson and so forth. And I would love to refer you to mixed precision algorithms in numerical linear algebra, recently published in Acta Numerica, for a very good review. Now, the renaissance that we are pursuing is combining both of these ideas, as I mentioned, within the same data structure, and in a typical million by million covariance matrix, which would be a trillion unknowns. If they were 8 bytes, that would be 4 terabytes, accounting for symmetry. We can replace that with no practical loss of accuracy in our optimization process for max likelihood estimation in statistics by a matrix that costs only less than a quarter to store. That means larger problems fit in GPUs and last level caches for data movement savings. There's also computational savings, although that's almost incidental compared to the time and energy costs of data motion, whether between processors or up and down memory hierarchy. Of course, data structures and programs are more complex, but that's what we're for, to present a nice API to the users. Now, I just will remind you of some of the complexities of rank structured factorizations. Tile low rank is not the only game in town. It does replace an n or a half power of n in storage with a square root of the typical maximum block rank. And there are also much better algorithms in terms of complexity in the hierarchically low rank regime, which actually go back much earlier than these tile-based algorithms, but of course are much more complicated to code because it's not just a flat division into tiles, but hierarchical subdivisions. And these are also very popular now and entering into software. Whether we're talking about operation count or storage, dramatic improvements, orders of magnitude are possible for very common operators. So rank gives us, in effect, or block rank or hierarchical rank in those algorithms, give us a tuning knob for matrices, whether they're born dense or whether they arise as dense blocks during sparse matrix operations, ensure complementation. And we can use high accuracy, high rank to build exact solvers, low accuracy, low rank to build preconditioners. We can consider hardware parameters to our advantage in tuning such block sizes or maximum rank tolerant parameters to complement the mathematical considerations with hardware optimizing considerations, such as things that fit in cache or things that occupy a warp. And we can select from a broad and ever broadening algorithmic menu to form these low rank blocks from their dense equivalents. In fact, they can often be formed on the fly without ever forming or storing the dense matrix original. And of course, what we have going in our favor is that these are built out of vendor optimized gems. So we just express everything in terms of gems at the lowest level, and we ride the hardware wave. And of course, if they're fully hierarchical, like in fast multipole analogy, we will have to implement them in batches of leaf blocks for efficient use of GPUs. Low rank approximations for compressible tiles. Standard SVD is order n cubed for the block size n, probably too expensive. Randomized SVD gets rid of one of those powers of n, makes it comparable to other of the dense manipulations, and is very useful. There are even more abbreviated, more approximate versions like adaptive cross approximation, which get rid of 2 powers of n for 2Ks, and other matrix skeletization using representative collections of rows and columns, all of which are very exciting mathematical frontiers, depending on your tolerance for accuracy. The algorithmic opportunities for such, the application opportunities, I should say, for such algorithms are those with memory capacity constraints like geospatial statistics or PDE constrained optimization like seismic inversion, power constrained operations like remote telescopes where you have to do adaptive optics, wireless communication, which has a real-time constraint where you can cast decoding into fast matvex, running time constraints where there's not that much scalability in the standard methods like chemistry and materials, and the ever increasingly important genome-wide association studies, millions of patients, thousands of traits, trying to find correlations, or in, for instance, adaptive agriculture, where you have many different genomes of rice or wheat or quinoa or whatever it is, and you're trying to find environmentally favorable traits for our arid saline world of agriculture. Now, dynamic task graphs need to be brought into play for handling the algorithmic adaptivity here. I'm not going to go into the software, just to mention 3 of those that are open source that we partner with in various groups. So now let's get into our example, which is, say, a climate weather application where we want to optimize the parameter fits theta for a scalar L, where we have this triple product involving the inverse of the covariance matrix and its log determinant, both of which are available as byproducts of a Cholesky factorization. And we can divide we can take a set of training measurements, observations. We can withhold some as test sets, and test, our algorithms. And just to compare the HICMA tile low rank, for example, versus standard dense Cholesky with optimized Intel MKL on Intel's own hardware for 3 generations, you see the n cubed growth on this log curve with matrix size on the x-axis for the traditional method, and then the same hardware generations with the improved algorithm. And the red is just using the same algorithm on the improved hardware. The green is using a different, the improved algorithm. And then the blue, which is additive in this log scale and multiplicative in real life, you see is about 2.5 orders of magnitude, about 2 from the algorithm and about 1/2 from the hardware improvements. What about the memory footprint? Well, if it's 1,000,000 by 1,000,000, that's 4 terabytes stored symmetrically. And you can see another couple of orders of magnitude available from different accuracy tolerances in your synthetic and real data. What about distributed memory? Again, going from 16 to 256 nodes following the colors of the scale-a-pack method, we can beat the 256 node version with just 16 nodes of the Cholesky tile low rank, for example. What about the efficiency? We've been talking about scientific efficiency, which is reflected in the 10x improvement in runtime. But I would like to point out to you that the tile low rank algorithm is much less parallel efficient and much less percentage of peak delivering because of all that red, where certain processors are idle waiting for data. So this amazing reduction in flops doesn't make the algorithm look as good, but we have to, be careful when we think about performance to what is really the scientifically relevant criteria. This is just an example of an extreme tile low rank application on our Shaheen supercomputer, 42 million degrees of freedom on 4K nodes. It would require 7 petabytes if stored densely, and it would require 77 days by the scale-a-pack algorithm at the TLR flops rate. I would point out that this would cost $1 million of electricity and generate 2,500 metric tons of CO2 if done using dense double precision Cholesky. So I hope case made, 2 orders of magnitude improvement. Another motivation for mixed precision is the amazing hardware capabilities coming to us from vendors like NVIDIA and several more entrants into GPUs. When you go from 64 to 16, from double to half precision in the tensor core, you don't just get a factor of 4, which you might expect from data motion. You get factors of 8 or 16 in the latest generations, including the Hopper, which will be released next year, delivering an amazing petaflops on a single tensor core if you're willing to use half precision. And half precision is perfectly acceptable in many scientific fields, just as it is in machine learning. One example from our recent paper, Responsibly Reckless Matrix Algorithms for HPC Scientific Applications, in the special issue dedicated to Jack Dongarra, coming up, of Computing in Science and Engineering, the IEEE journal zine. You see here plotted in flops, and it's only a linear scale because precision doesn't give you as much as rank in these things, but you can see 3 generations of NVIDIA hardware in the dashed curves, and the latter 2 with a double precision, half precision mix, giving 10 to the minus 9 accuracy in each tile and an overall factor of 10x in runtime from the oldest hardware and previous algorithm to the newest. Mixed precision geospatial statistics on distributed memory. If you just follow the blue curves from 4K nodes of Shaheen to 1/3 of the number of nodes of Hawk at HLRS to just 128 nodes of Summit at Oak Ridge, you see comparable 4.5 teraflops performance and a factor of up to 2.6 in overall speedups. So now, with almost no time left, I will do a brief preview of one of the 2022 Gordon Bell finalists, emphasizing these kind of operations in the geostatistical regime. This is joint work with the Innovative Computing Lab at UTK, and of course, where Jack is this year's Turing recipient. So here's the paper, its title and its attributes. The performance results are yet to be improved with more access to high-end machines, but we have some 2D data and some 2D plus time temporal data from environmental statistics. The goal here, of course, is to do statistical emulation using known observations or simulated data to infer at unknown locations. This is, of course, increasingly critical in predicting demands from weather, engineering safety margins for storms, mitigating hazards, citing renewable resources where they'll continue to work as the climate changes, and so forth and so on. These are major supercomputing workloads these days. And whereas simulations based on PDEs, like running an ensemble and taking Monte Carlo averages, are usually intensive and memory bandwidth bound, emulations based on covariance matrices, they build some knowledge into the low dimensional fit and are usually thrust into the compute bound regime where machine learning has made our hardware efficient. I'll call this a challenge or an opportunity. It's a challenge to the statisticians. It's an opportunity for us as their data sets become increasingly large in number of locations and as they move into multivariate correlations where you might, for instance, try to infer the soil moisture from the temperature because you have more temperature measurements than soil moisture measurements, for example. And the statisticians have been watching with great delight their observational power increasing while their computational power begins to bound them to really primitive methods like global low rank or zero outer diagonals, and hierarchical low rank and reduced precision outer diagonals are the way to go. And you'll remember that a million by million dense matrix stored in double precision with symmetry occupies a 4 terabyte drive. You know how long it takes to write your own 4 terabyte backup drive. We got testimonies from many famous statisticians about the virtues of getting, double precision useful results from mostly half precision storage, reducing memory footprints to allow larger data sets, and encouraging more statisticians onto HPC resources from their traditional R, for example. I won't go into the software that we use called exageostat. I do want to do a shout out to Sami Abdullah, the lead architect. You see there in the middle the DAG for a tile-based Cholesky factorization into which the low precision and the low rank conversions of the dynamic data structure have been set. So exageostat generates synthetic matrices, it does the MLE, and then it does, if you will, the inference. It then does the Schur complements on the unknown locations from the spatial covariance matrix. This has been ported to many of the world's top systems based on A64FX, NVIDIA V100, AMD EPYC up to Milan, and Intel x86 up to Sapphire, and so forth. Since it builds on GEMS, it's very portable. This is again the optimization problem. We use NL-opt from Steve Johnson as the traditional optimizer. We've also experimented with hierarchical forms of parallelism, where several different large problems are happening in parallel, as in the parallel swarm method. They are data parallel. I mean, they are embarrassingly parallel with respect to each other. We have many kernels, many assumed kernels in exageostat. The two that are in the Gordon Bell paper are a Matern kernel for the spatially only problem, and the space-time non-separable kernel, which has 6 parameters to fit. Tiles are compressed to low rank based on a user supplied tolerance, and the tile-centric structure is decided at runtime based on the rank whether to convert back to dense double. So this is based purely on complexity considerations, while the precision is based on mathematical considerations from the recent Hyam and Mary paper, which shows, and I'll get to the bottom line, that you can get your tiled matrix, the script A, its Frobenius norm can be bounded, the difference of its Frobenius norm with the true full precision A can be bounded away from the original matrix A norm by the machine epsilon of the high precision, while you are allowed, if I can back up, to replace your tile with in any block with a lower precision version, as long as its local Frobenius norm times the number of tiles per dimension is less than the ratio of machine epsilons. And this can be carried out to multiple levels of precision, not just single double, but half single double and so forth. So just I'm getting to the end here, just to show some evidence. There are 27 box and whisker plots on this. They go from weak to strong correlation from top to bottom, from the 3 different parameters of the 2D Matern kernel from left to right. And within each box, the dense default double precision, and on the right, the multi-precision dense tile low rank. And you can see that the parameters are fit fairly well by the cheapest method. And this is your interpretation of the skewing of the box and whisker plots. But what is really more important is the mean square prediction error, which for all 3 algorithms, despite their orders of magnitude difference in memory footprint and runtime, give practically the same result at the output of interest, the same log likelihood scalar, the same mean square prediction error. So, we've had some access to Fugaku thanks to Riken, and you can see in red here, the largest problem that fit in 16K nodes for dense double precision. And you can see that if you go to mixed precision plus tile low rank, you can run that same problem, same size problem in 3 times less time. Or if you are willing to do the same amount of time, you can solve a problem 3 times greater in size. This is yet to be improved because our dynamic runtime system is actually a pretty big memory hog on memory constrained A64FX, but this should not be a problem much in the future. These are the footprints of several of the real correlation matrices that arose. They all improve on the default double, although the very strong correlations are, of course, not as good. So this is the end of my talk. We are building, we hope, the algorithmic infrastructure that mediates many applications with dense linear algebra that can be ordered into data sparse blocks on many different architectures. I recap my conclusions that HPC people have an incumbent upon them to get extreme efficiency out of exascale extreme computing in order to stay affordable and not to violate really morally our climate crisis. For follow-up, and these slides will be posted as well as the movie of the talk, I highlight several, papers going back to 2018, but mostly quite recent ones, including the Hayam review at the bottom. I want to do a shout out to all the collaborators on the Gordon Bell paper, and especially to thank the Chaos Supercomputing Core Lab for use of Shaheen, for HLRS Stuttgart for use of Hawk, and of course Riken for use of Fugaku. And I'm embarrassed to have omitted Oak Ridge, where we had a lot of very courteously afforded development time on Summit, and look forward perhaps to time on Frontier. So thank you, shukran. And if you wish to pursue energy efficient computational science with us, we would love to consider you. But you can send an email to my host here, Hatem Altayev. And now I turn it back to our officers for what I hope will be a fruitful Q&A. Thank you very much.
Great. Thank you so much, David, for the great talk. So let's see, we have a few questions online. Let's see. So the first question is from Horst Simon.
Uh-oh.
So how do you deal with the rebound effect? If you provide more resources, you will increase consumption. HPC users will take advantage of the more energy efficient algorithms to compute more and attempt larger problems. So the typical example is if you build more freeways to reduce traffic congestion, you will get more suburban development. In energy economics, this is called the Kazum-Brooks postulate. Energy efficiency leads to increased energy consumption. What is your take on this?
Yes. Well, Horst, yeah, you're right. In fact, when we went from Shaheen 1 to Shaheen 2 here with about a 25-fold capacity improvement back in 2015, instantly all the oceanographers and atmospheric modelers just, doubled their grids in each dimension and soaked it up. One could argue that at least you're getting more science for the same expenditure. But yes, it is definitely an issue. And I would encourage all of us to rethink what we really need to compute. As in the example of the output bound analysis earlier. We often don't need to solve the PDE to high accuracy everywhere. We often don't need to solve anything to high accuracy in the inner loop of an outer loop problem, like a nonlinear solve or an optimization problem. And we need to bring a consciousness of this into our everyday computing, because the applications people, of course, are just going to look for that API and want to do more and more with the more that we give them. But yeah, it's a great question. I confess I don't have a behavioral science answer to it.
Great, thank you. Next question from Thorsten Hoffler. Thanks for the great talk. Lower precision accelerated computations significantly, but data movement less. Now, new algorithms may be more data movement bound. How do we deal with this new bottleneck? Do you have any algorithmic idea?
Well, my only simple idea in immediate response to your very good question is that when you reduce the overall size, your working sets fit, higher and higher, or what you might say more and more locally, so that the number of data motion copies or barriers that you cross for the same size problem can be reduced. As you know, data motion being much more expensive than computing, this is really where the game is. It's not just a question of, matrices. There are better basis functions in, for example, density functional theory, or, there are many places where representations of the same physics or biology or whatever can be sought with a more efficient mathematical model. This has an immediate effect on data motion reduction, but in terms of the more sophisticated things that you may have in mind, in terms of, cache policies and, multi-level buffer systems and, various double buffering algorithms, there's many computer science tricks that are designed to sort of mitigate the big energy and time boundaries of crossing memory hierarchies, and they are hopefully orthogonal to the mathematical tricks, so that we can derive a benefit from both. I hope I weaseled my way out of your hard question.
All right, a question from Andrew Kniazev. Silicon photonics already breaks communication records and is arguably an upcoming revolutionary change in low power computing hardware, but is commonly limited to 8-bit precision, being analog technology. Could it be still useful for numerics?
Wonderful question, Andrew. One that I did not know about. I mean, I know that optical computing is coming. I'm a good friend of Karen Bergman's, but your quantification of what's coming is very interesting. 8-bit, we know that works for certain machine learning things. It's better than 0 bits, in terms of, it's only quarter precision and, not much mantissa if you make it floating point. It's a very good question. We'll have to see when given such a tool where it's acceptable. I think one of the most amazing discoveries of recent years in large-scale simulation was that all the weather models that we've been doing, in NCAR and WMCF and so forth, can be moved over to single precision with very little loss of accuracy. We should have done this many years ago, and it remains to be seen how many applications can actually take use of the hardware that machine learning forced upon us. yes, we have to do things better than decide whether something is a dog or a cat. We often have to interpolate continuous functions. We do have to deal with ill-conditioned operators, and where those arise, we have to be, really conscious of it, or we throw out the entire computation with some weak link in the chain. But there are many links in the chain that are made much more stronger now than they need to be for a given output. And so I do look forward to what optical computing will give us in this regime.
Awesome. Question from Hiroshi Murakami. Give us the idea how much percentage of budgets are allocated between hardware installation and software development.
Actually, I am on a DOE advisory panel at the moment for the first time in several years, but I haven't looked at such budgets. Of course, the DOE labs are a good place to look. One could, estimate. I mean, the acquisition cost of Fugaku is well known to be on the order of $1 billion, and for several years leading up to putting Fugaku on the floor, Riken was working on the apps to go with it. There were maybe about 8 or 10 apps, each with a large group developing the modeling and simulation and the software in anticipation of the tensor core and other capabilities of A64FX. I don't know how much those integrate up to, so many groups over so many years compared to the cost of the machine or the, on cost of running it day by day with electricity prices where they are. I would urge someone in lab land right now to tabulate those and see whether we have many false economies going. If you think about, a 4 million savings out of a 40 million power budget for 1 year, that pays for a lot of people, even at high lab overheads.
Absolutely. One question from Matthias von Waveren.
Hi, Matthias.
Have you looked at quantum algorithms? These algorithms also can have a reduced complexity compared to classical algorithms.
Yeah, I mean, phenomenally so when n gets large enough. So far, it appears that for very few problems do we have enough qubits to take n large enough to make it worth the algorithm leap. But of course, we should be vigorously studying those algorithms because there will be Moore's law for the 5 or 6 different relevant quantum qubit technologies, whether they are optical or cold trapped ions or Josephson junction, whatever they are. We have to be ready with the algorithms. There are, 300 algorithms at the Quantum Algorithm Zoo at the National Bureau of Standards, which already have tabulated the, in many cases, exponential, in other cases, algebraic advantages over their deterministic equivalents. But most of them cannot be verified yet in real runs because we just don't have, the noise-free hardware. But yeah, I love all of these questions so far. They're all so SIAG. I mean, everybody's thinking ahead and giving good ideas to the students online. And yeah, thank you.
A follow-up question from Thorsten. Have you considered robust PCA, low rank plus sparse, as a theoretical framework for the compression of matrices?
So principal component analysis.
Yes.
I see. So you mean like globally low rank? Yeah, like PC. Okay. We have not. Omar Gattas has been championing that for many years in Hessians. Hessians typically can be represented as a low rank piece plus a sparse piece. And in fact, we have one paper with him where we compared that with a more block low rank approach, and the block low rank won. I mean, but there's no question that the global low rank plus extra piece to make up for the fact that these matrices really do have full rank, that is a very strategic data structure without question. I've never looked at how the precisions would affect that, but yes, that's been proven effective for Hessians and maybe for many other, maybe for second order methods in machine learning, who knows? It's an alternative that we have not pursued.
Great. Question from Ben van Verhoeven. Thank you for the very nice talk. I was wondering what influences the decision to reduce to the precision in certain blocks more than in others.
Yeah.
Is this data dependent or inherent to the domain decomposition? How often do we run to retune the precision of these blocks?
Right. So very good question. So the precision is based on this Hayem criterion that when the Frobenius norm of your block times the number of tiles per dimension is less than the Frobenius norm of the overall matrix times the ratio of the precisions, you're entitled to ramp down the precision of that block. And this can be applied recursively. Now, this is certainly a reliable kind of a heuristic for matrix multiplication, which is the core of many methods that involve all kinds of linear algebra. Whether there are recursive effects in a factorization method from this kind of precision reduction in blocks is something that I think the community needs to investigate. We are investigating, if you will, empirically or experimentally. We compare the results of the final optimization when running 10 times more efficiently with the results of the default double, and we have discovered that in some cases for really highly correlated problems, we need to drop back. But I would say in general, the heuristic serves us very well. And I believe that there are many, sort of theoretical numerical analysts looking at a posteriori bounds on such, let's say, efficiency obtained from lower precision these days. Remember, there's many kinds of low precision or mixed precision algorithms now that give results worthy of the highest precision with most of the ops done at lower. They include direct factorization methods, they include Krylov methods, they include traditional, iterative refinement, they include mixtures of Krylov with various factorization preconditioners. There's really a huge alphabet soup of such mixed precision methods, all of whose goals are satisfy the user tolerance at the final answer, and use as short a set of flops, of mantisses as you can en route. And I'm sure that there will be some lessons learned. I'm sure there'll be a few catastrophes along the way where the right post computation bounds weren't verified. But it's the wild west, and to the extent that it will give you more science per unit flop or joule, I think we should be looking at it.
All right. I guess with that, we almost at top of the hour. We'd like to thank our speaker today, Professor Keys, for entertaining us for an hour. Amazing, talk and discussion, engaging with the audience. We're really excited about it. So we'd like to thank everyone for attending the webinar. And please stay tuned. We'll send the slides and the material, the videos on our social media. We'll get back to you shortly. Thank you so much, everyone. Bye-bye.
Were you going to flash the survey slide?